Welcome to Algebra 2. Today we've got section 6.3, logarithms and logarithmic functions. Now, as with a lot of this material that we've covered so far this chapter, maybe some of it has seemed familiar. This might be one of the first big concepts we've had that you haven't seen anything about before. Logarithms. And the concept itself makes perfect sense, I think, once it's explained to us, but it sounds really intimidating. So I want to alleviate any fears. Don't be intimidated by the fancy language here with logarithms. It's not a difficult concept. All right, so since it's our first time seeing this, well, what is a logarithm? Well, one way to think of a logarithm is that it's a means of undoing an exponential function. It's behaving like an inverse in that capacity, so we can have logarithmic functions that undo exponential functions. Okay, a logarithm itself has two parts, the base and the argument, and you can see that shown below. We've got a little subscript here, that's our base, and it can be a number, or it can be, sometimes not expressed at all. That's implied to be a base 10. Then here we call this the argument. It's the input area of the logarithm. And so we read that as the log base b of n is a. So log base b of n to describe it. All right, well, since this logarithm idea is a way of undoing an exponential function, well, think about how an inverse would behave. So how is that working in relationship to these exponential functions we've covered so far? Since an exponential function has an exponent as its input, and we just said logarithms undo exponentials, a logarithm has an exponent as its output. So I call this def log, but our definition of a logarithm is the perfect exponent to turn the base into the argument. Okay, so if let's say we've got log base 4 of 17, what that's saying is the logarithm itself, the whole thing, is the perfect exponent to put on a 4 to turn it into a 17. What will turn the base into the argument? So a logarithm is an exponent. A logarithm is an exponent. So we can easily convert a logarithm into some exponential expression. So if we said that this log base 4 of 17 is equal to x, then that means 4 to the x power equals 17, because that x represents that perfect exponent. Now the output of the logarithm is the input of the exponential. That's that inverse-like relationship. All right, so one place where you may have seen logarithms before is science class, particularly with chemistry. I believe you use logarithms quite a bit there. On your calculator, you're familiar with a log key and ln keys. And those refer to common logarithms and natural logarithms. The common log is understood to be a log with a base of 10, very useful when we're dealing with scientific notation. And ln, or the natural log, is equal to a log with a natural base, log base e. So we won't always see the bases written, but we can understand they're understood to be there. Okay. All right, so we talked about how logarithms undo exponentials. They have this like inverse relationship. So graphically, when we talked about inverses in chapter 5, we talked about how a function and its inverse, when graphed simultaneously, will show symmetry about the line y equals x, because they're switching their x's, their inputs, with their y's, their outputs. So if you think about what our exponential functions look like, and we'll use this first picture here to illustrate. Here we've got an exponential growth function right there, and we know it had a horizontal asymptote, right? Y equals 0 was that horizontal asymptote. Now when we look at the graph of our logarithm that has that symmetry across y equals x, right here, because we have flipped the roles of x and y, a logarithm has a vertical asymptote at x equals 0. And again, this could change based on how the graph is shifted around the coordinate plane, and we'll talk about that in section 6.4 here coming up. But the basic idea is the asymptote does switch. And that kind of goes with a little bit of a restriction on our logarithm, because if we have this vertical asymptote at x equals 0 right here, it's saying that I can't plug any negative x values in. So you can see that the only inputs that we have are ones that are greater than 0. So the domain of a logarithmic function has a restriction on it, but the range is all real numbers. Again, if you think about what domain and range looked like for exponentials, we could put anything in that we wanted, but then we had restrictions on what came out. Well, since we're flipping the roles of those inputs and outputs, now there's restrictions on what we can put in, but we can get anything out that we want to. So a little bit of a relationship there with inverses and why these two really go hand in hand in our class. All right, our first task is to establish the pattern, establish def log, the definition of a logarithm, just by converting an equation that is a logarithmic equation into one that is exponential. All right, well, what 6 is saying, my logarithm, my perfect exponent, is a 1 if I wanted to turn a 4 into a 4. So I would write that as 4 to the first power equals 4. Now, one way I've taught this before in years past is I've drawn arrows to kind of show the way through the equation. My base of 4 to whatever the logarithm's equal to that power equals the argument. So 4 to the first equals 4 is what we would say there. For problem number 8, here, my base of 3 to the negative first power will get me to 1/3. Or I could think about that as 3 raised to that perfect exponent that our logarithm is saying is a -1 will produce a 1/3. And it goes without saying that these are equal. We are just rewriting them in a different format. All right, number 14, now we're working backwards. And you can see that in our exponential, we have a base, we have our perfect exponent, and we have what that base to its perfect exponent is equal to, what it's making. So I know I've got a logarithm. The base it's raised to a power is 5. It's turning into 1/25th, and we said that this perfect exponent was equal to a -2. And I might just real quickly check through the pattern to make sure it's leading back to where I started. 5 to the -2nd power equals 1/25th. Yes, that's what I started with, so I can be confident in that answer. Number 16, here we're taking a log with a base of 49. It's turning into a 7, and that perfect exponent to turn a 49 into a 7, they're telling me that's 1/2. A quick check through the pattern, 49, the base, to the 1/2, that perfect power, equals 7. So yes, that is what we started with, just getting some familiarity with the pattern, the definition of a logarithm. Okay, example 2, evaluate the logarithm either by using the definition of a logarithm or a calculator. If you understand how logarithms work, then this is a very easy process. However, if we don't necessarily understand, then a calculator can be a little bit of a help to us. We won't really find out how to enter most logs until we get to 6.5. So they really want us to understand how to make these work without the need of a calculator, if at all possible. Number 18, I'm trying to find out what this logarithm is equal to. All right, so what is this logarithm equal to? Well, I'm trying to turn a 7 into a 49 with some exponent. 7 to what perfect power will make a 49? Well, let's think. That means 7 to the x would equal 7 squared. Oh, so my x has to equal a 2. And all I did there was I rewrote 49 as 7 squared. Okay, and we may be able to do it without requiring this step. We should probably know that that x has to be a 2 to make that statement true. Let's try the next one. Okay, I'm trying to find what perfect exponent this logarithm represents. So 8 to what perfect power will make 1 over 512? Well, I'm pretty sure, and a quick check in a calculator could confirm this, that I've got 8 to the x equals 1 over 8 cubed. And, oh yeah, I remember from chapter 5 that says if I have a term with an exponent that's in a denominator, I can express that as a negative exponent. So really how I could think of this is 8 to the x equals 8 to the negative third. So that perfect exponent has to be a negative 3. Okay, and we'd probably run that through a calculator, make sure that 8 to the negative third is 1 over 512. But just understanding the pattern is really, really helpful. All right, now number 30. Here, there is no base written, so it's understood to be a log base 10 of 2/7. So I'm thinking 10 to what perfect power would give me 2/7? Right, that perfect exponent is what we're looking for. And 2/7 is definitely not some power of 10, so unfortunately I am resigned to using the calculator on this problem, and really it's not all bad because it's a log base 10. I can just use the log key on the calculator. So I'm just going to type in log 2/7 equals, and I get negative 0.5441. Okay, and I did round that, but that is the decimal expression for what that logarithm is equal to, that perfect exponent is equal to. Okay, not too bad. Next, simplify the expression. Again, hopefully solidifying the idea that logarithms and exponentials are inverses of one another. So we're going to use the definition of a logarithm here to help us out. All right, so 36. This problem says I've got 3, and it's raised to the power, and this power is the perfect exponent to turn 3's into 5x's, right? So if I have 3 raised to that perfect power, then what's going to come out is the argument, 5x. All right, so what we can take away from this, the pattern that's working, is when I have an exponential base and it's raised to a logarithm with that same base, that's where the inverse works. Okay, if that exponent was log base anything else, we wouldn't get that nice cancellation to happen. But our answer is just 5x because we're taking a base of 3 and raising it to the perfect exponent I would stick on a 3 to turn it into a 5x. All right, so I don't like doing this, but essentially that's what's happening. The 3 to the and the log base 3 are canceling each other out, leaving us with just the argument. All right, let's take a look at number 40. So I've got the natural log of e to the x plus 1. Well, that's like saying log base e of e to the x plus 1 power. All right, so now I'm thinking this is representing the perfect exponent to stick on an e to turn it into e to the x plus 1. Oh, well, I should be able to look at this and understand what has to fill in this little dashed circle here. The simplified expression should just be x plus 1. That is the exponent I want to put on e. Okay, so another type of inverse relationship is if I have a logarithm with a certain base, and inside its argument is that same base raised to some power, then I get that inverse action to happen. Okay, and in this case, since a natural log means log base e, and my argument is e to something, my answer is just going to be that something. The inverse relationship takes place. Okay, it might seem kind of out there at this stage of the game, but I hope we can realize how these two types of functions are working in concert. Okay. Example 4 says find the inverse of the function. Well, if you remember back at the end of chapter 5 when we found inverses, what we wanted to do was flip the roles of x and y. So let's see what's happening here in number 46. If I flip the roles of x and y, I get x equals log base 1/5 of y. And if I solve for y, I would use the pattern, the definition of a logarithm. Def log says 1/5 to the x equals the argument of y. So 1/5 to the x equals y. And again, we kind of reiterate that idea that a logarithm with a base of 1/5 is undoing an exponential with a base of 1/5. Let's try number 50. If I flip the roles of x and y, okay, well, here I've got an exponential, and if I wanted to solve for y, man, that would be kind of a tricky endeavor to do. So let's think logarithmically. I know that a logarithm is inverting the work of an exponential. So I know that a log with a base of e, to turn it into an x, has to be a perfect exponent of y minus 4. So again, we're using the definition of a logarithm just kind of in reverse here to create the logarithm. And if I solve for y, all I would have to do is add 4 to both sides. So y equals log base e of x and then plus 4. And we probably want to put parentheses around that logarithm just so we know that we're not including x plus 4. Not all of it goes inside, just the x goes inside. And we do have one more step, a log with a base of e. We call that natural log x plus 4. So we should replace log base e with ln. Okay, and our final slide. Graph the function and determine the domain, range, and the asymptote. All right, well, we know logarithms have vertical asymptotes, so graphing these logarithmic functions should not be terribly difficult as long as we remember that they generally take this shape. Okay, and we got that idea when we looked at the parent functions earlier in this lesson. Well, it would be nice to be able to set up a table of values. That's what we had done before. And we are going to do just that. The idea is I want to set up an equation that's an exponential. So I'm going to use the definition of a logarithm to do just that. So the function I'm given says 3 to the y power becomes x plus 2. And from that, I can say that x is equal to 3 to the y minus 2. I would subtract 2 from both sides. And now, since I'm dealing with an inverse, you can tell that my x and y have been switched. That's what logarithms do. I'm going to choose y values. And I'm going to run those through my formula there to find the x values that go with them. All right, so I'm going to use a calculator to help me out with that. Just kind of speed up the process here. So I've got 3 to my input and then minus 2. And if I look at my table, I get the following. When my y value is -2, my x value is -1.9. When my y value is -1, I've got -1.7 for an x. When my y value is 0, my x is a -1. My y value is 1, my x value is 1. And when my y is 2, my x is 7. So I get some quality points from the graph, and yes, we're going to have to approximate a little bit, but hopefully we're seeing a nice little pattern here set up. So let's see, I'm at -2 down, or at almost -2, -1.9 down at -2, right there. -1.7, I'm down at -1, right about there. -1, 0, the 0.11, and then the 0.72. Sure enough, we can see that graph. And if we wanted to grab more values out of our table, or try some more x values or y values, we definitely could. But just determine the domain, range, and asymptote. Well, let's find that asymptote first. Remember, in a logarithm, our asymptote is going to be a vertical one. So here I've got x equals -2. Okay, and if you're wondering why, it's because this input has to be positive. So I set that greater than 0 as an argument and solve it. I would subtract 2 from both sides. So to zero out that argument, that's where the asymptote will occur, because a logarithm cannot have 0 for an argument. It can get right up to it, but it can't have a 0 or a negative argument. Okay, the domain is pretty easy to spot from our graph. It's all x values that are greater than that asymptote of -2. And my range, well, all real numbers. Again, just kind of flipping the roles of our exponential graphs from the past couple sections. Let's take a look at 64. If I were to write this as an exponential, well, first thing I need to do is subtract 3 from both sides. And I'm going to call that log base 10 of x. No base given, that's understood to be a common log. Then I need to divide both sides by -1. And this is all to help me set up a table of values. Then I'm going to run through the pattern. 10 to the -y plus 3 power, all of that is the exponent, right? The base of 10 to that perfect exponent creates x, and we can set up our table of values. But remember, now we're solving for x's. It's an inverse type of relationship. So I'm going to pick the y values that go in. Okay? And between -2 and 2 are pretty good choices, at least to get a general idea. So I've got 10 to the, in parentheses, negative input plus 3. And let's see what we get for a table. Oh boy. At -2, I've got 100,000. At -1, I've got 10,000. At 0, I've got 1,000. At 1, I've got 100. At 2, I've got 10. And I better put in some more y values here and find the x's that go with them. When the y value is 3, my x is 1. And at 4, my x is 1/10, or 0.1. So let's see if this kind of agrees with what we feel like a logarithmic function should look like. So let's see, when my x is, well, I'm not going to be able to graph it until I get to this one right here. X is 10, my y value is 2. When my x is 1, my y value is 3. When my x is 0.1, my y value is 4. So I'm seeing this type of thing happen. All right, does that make sense? It looks like exponential decay almost. Well, our asymptote, well, what would zero out the argument of my logarithm? It's when x equals 0. All right, my domain, I want all x values that are greater than that 0 asymptote, because I see all my graph, all the values on my graph are showing up to the right. And the range, again, will be all real numbers. And even though this looks like exponential decay, we are seeing a vertical asymptote, and you could look at your calculator's graph as well. That would confirm that there's a vertical asymptote happening, which is our first big indication that it's not an exponential decay. But then also just look at the function we were given, y equals 3 and then negative log x. That is like a logarithmic function like we saw in number 60, but with a vertical flip and shifted up 3 units. Now that starts to make sense. So that transformation stuff is really helping me to kind of piece together this graph. Does it make sense? Yes, it does. All right. That does it for examples. Here's a look at your homework assignment for 6.3. Really take some time to understanding the definition of a logarithm. A little time investment right now to understand it is going to pay off big time towards the end of the chapter and later on in math classes. And just understanding the relationship between logarithms, logarithmic functions, and exponential ones. That inverse relationship really does help us out. So again, that's the end of section 6.3, and we'll see you next time.